Okay, so now what we really want to do is to prove that the thing that we've got for this category set to the power of c really is a subobject classifier. So the first result we want to prove then is this classifier theorem 1. In set to the c, if we have an arrow a into omega, then I suppose we have this inclusion monic a star, which is the pullback of true along a. Now, the claim is that the source of this inclusion monic, Q, has this set of E-type elements, which is just the set of theta in AE, which is such that A subscript E of theta is psi E true. And remember, psi E true is just like, if we're thinking of it as a subobject of Hom E, then it's just the maximal subobject of Hom E comma blank. Okay. So it's basically a pretty simple idea. We're just saying that the stuff which is classified, so it's a pretty simple idea. Basically, we're just saying that the if we just look at what kind of thing, because these are sort of like the elements in omega which sort of correspond to true, and we're basically just saying that if we look at the different components, say we look at the ETH component of A here, and we look at the things that ascends to these kind of E-type elements of omega, which correspond to true, they're the things that are going to be present in this kind of subobject, which is the pullback of true along A. So how do we prove this? Well, suppose then we have this inclusion monic A star, which we can write as A to the minus 1 of true, considered as an inclusion monic. Well, in that case, this red star formula here, because I mean, if we're thinking of that arrow true from 1 to omega, if we're thinking of that as an inclusion monic as well, then we're essentially pulling back an inclusion monic to get an inclusion monic. And so we have this kind of formula for how this kind of thing works. Like, this formula is for the case where we're pulling back A along an arrow F. And we find that the set of E-type figures from this formula is just going to be the set of E-type figures in the source of the arrow that we're pulling back along, such that doing the ETH components of the arrow on such a figure gives us something belonging to the monic that we're pulling back along. Okay. So in our case, what this means for us is that, since we're basically pulling back true along A, and we're thinking of true as an inclusion monic, we're thinking of like 1 of E as just the set that just contains psi et and so on. Well, when we pull back true along A, that kind of result gives us that when we're thinking of this pullback as the inclusion monic, we have that Q of E is going to equal the set of theta in A of E, such that A of theta is in 1 of E. But as I've said, we're assuming that 1 of E is just this set which just contains psi et. So that means that we can rewrite this set here as the set of theta in A of E, such that A of E of theta is psi of E of t. And that's what we're claiming. Okay, so remember, this stuff is contingent on us thinking of this true arrow here as an inclusion monic. So like, in order for something to be a terminal object in this category set to the power of C, I know I said earlier that that it should be like the E-type elements of the terminal object should be a singleton set for every E. And I actually said, I think, when I was defining the terminal object, that each of those singleton sets should be the same. But that's not really necessary, actually. It's easy to see that if you sort of change the name of some of the singleton sets, as long as you have these unique arrows between them as the kind of lifted actions for the terminal object, the unique arrows between singleton sets being the kind of S action functions, then you'll have something isomorphic, which could also be considered a terminal object. So for us, to make things easier so that we deal with everything in terms of inclusion functions, we just suppose that the terminal object of E is the set of psi et. Just this sort of singleton set where, as usual, psi et denotes hom e comma blank, denotes the identity of hom e comma blank. And so, okay, this is really a subobject of hom e comma blank, but we think of it as an E-type element of omega. And so it's easy to see that we're making the terminal object from the psi e comma t thing, and that this is just part of omega, and we're thinking of t then as the inclusion monic. Now this works because if we apply the S action on omega to psi et, then we get psi vt. So this means that when we restrict the action that's going on in omega onto this kind of included subobject 1 here, we can just define the S action on the terminal object as the sort of restriction of the S action on omega. And this works because it is indeed true that the pullback of, when we do the S action on psi ET, this essentially pulling back psi ET along HS to the -1, and that indeed does give us psi VT, because we know that for an arrow Q into Hom V comma blank, we have that Q is in the pullback of psi ET along HS, if and only if HS Q is in the is in psi ET, but psi ET is just equal to the identity of Hom E comma blank, so this is always the case. So Q would always be in this pullback of psi ET along HS, so that means that this must be indeed the identity of Hom V comma blank, because the only subobject of an object that every arrow is in is the maximal subobject. So yeah, this all makes sense to set things up like this, and indeed we can then define this true arrow as just an inclusion monic. Then, as I said, we're pulling back this inclusion monic along A and assuming we're getting another inclusion monic, and so then the components of A star are just going to be inclusion functions. But then we can think of a set of E figures of Q, the kind of source of A star. We can think of such E figures as the set of theta in A of E, such that A of E of theta is psi of E of true. Okay, and we've proved that now. So, okay, on to the next one. This is more challenging, but this really wraps up the kind of understanding how the subobjects work in set to understanding how the subobject classifier works in set to the power of C. It's this classifier theorem too. So it basically says that given this arrow T from the terminal object to omega, we have that this is the subobject classifier of set to the power of C. And moreover, the classifying arrow of a monomorphism M from X to A is this arrow which we call chi of M from A to omega. Now this is defined so that for theta in A of E, we have that chi of M of E of theta is going to be the element of omega of E, which is going to be corresponding to this kind of inclusion monic which is the pullback of M along theta under arrow. Okay, so how can we see this? Well, I mean, basically what we want to do is we want to be defining the ETH component. I mean, we're trying to make the classifying arrow and we're trying to argue it does what it's supposed to do. So the first thing we want to do is to show that this thing is actually an arrow in set to the power of C. We want to show that it's natural. So why is it natural? Well, you see how it's defined. The ETH component of chi M sends an E-type element theta of A to the pullback of M along theta under arrow, and if we just look at this kind of what we hope is a naturality square, we start with a theta in A of E. If we do chi M of E on this, we get the pullback of M along theta under arrow. And then if we do the S action on this, well, we can use we know how the S action works when we are when we're working omega, doing the omega S actions, just pulling back along HS. So we can write this result as the pullback of the pullback. So if we get the pullback of M along theta under arrow, and then we pull that back along HS, then that'll be the result of doing these operations starting with theta going along the top and the right of this square. On the other hand, if we go the other way, we start with theta, we do A of S of theta, and then when we apply the V component of chi of M, well, in that case, we'd essentially be pulling back M along A of S of theta under arrowed. But then notice that according to the pullback lemma, we can rewrite this top expression here, HS to the -1 theta under arrow to the -1 of M, as just the pullback of M along theta under arrow after HS. And also, by the action lemma, we actually have that theta under arrow after HS is just going to equal AS of theta under arrow. So indeed, these things are equal, and indeed, chi M of E, indeed chi of M with components like chi M of E defined as I wrote here does give us a natural transformation. Oh, excuse me. So yeah, chi of M is natural. Now our next claim, and this is important for sort of establishing that this thing really is a properly working subobject classifier, is that chi M of E is going to send theta to psi ET, which we remember is the identity arrow of Hom E comma blank. It's going to do that if and only if theta under arrow is in M. So the proof of this for theta in A of E, by definition, we have chi M of E of theta is the pullback of M along theta under arrow. And now here's the thing. Notice then that chi M of E of theta is going to equal psi ET, as in this maximal subobject of Hom E comma blank, if and only if the pullback of M along theta under arrow gives this maximal subobject of Hom E comma blank. But we want to show that that happens if and only if theta under arrow is in M. But we have that here because theta under arrow is in M. Well, we can rewrite this to say that the identity of hom e comma blank after theta under arrow is in M. And that then happens, according to the way that inverse images work, that just happens if and only if hom e comma blank is in the pullback of M along theta under arrow. And that happens if and only if hom e comma blank is equal to, or well, at least equivalent to, the pullback of M along theta under arrow, because the only way that a maximal subobject is in an object is if that object is equal to it. It is itself maximal. Okay, so we only have an identity arrow in a monic if that monic itself is the identity arrow, or at least, an isomorphism, a maximal subobject, essentially. So yeah, that does that. And this is really important because we can combine this. Sorry, this here in orange, this is really important because we can combine this with our classifier theorem 1 to basically show that chi-m does what it's supposed to do. That, we can basically pull back true along chi of m to get m, or at least the way I talk about it, we get an inclusion monic equivalent to m. So, okay, we have this result in orange established. So then classifier theorem 1 tells us the pullback of true along chi of m gives us an inclusion monic, which we can sort of write as a monomorphism z, an inclusion monic indeed, from z to a, with its E-type figures, so with z of e equal to the set of theta in a of e, which is such that chi-m of e of theta is equal to psi e true. But we know that this is equal to psi e true if and only if theta under arrow is in M. So we can rewrite this as the set of theta in A of E such that theta under arrow is in M. And now by inclusion lemma 3, we see that in fact this is exactly the form of the inclusion monic, which is equivalent to M in the first place. Okay, so we've now shown that pulling back true along chi of m gives us something equivalent to m. I mean, if you think about it, it's pretty clear that there's only a unique inclusion monic which is equivalent to any given monic, because once you insist that all of the kind of functions involved in the monic, each component of it as a natural transformation, are going to be inclusion functions, that means that you only have, they all just have to have this particular form as inclusion functions, and the stuff that they are including is uniquely specified because our inclusion lemmas basically say that, you have to have the kind of E-type figures present in this inclusion monic, precisely those which correspond to the kind of theta under arrow which are in M. And so that means there's only sort of a unique inclusion monic which is equivalent to any particular monic M. And so basically we've sort of almost done now. We've proved that we've sort of shown that we can make this classifying arrow which does what it's supposed to do. But the other thing we have to establish is that this is a unique classifying arrow. And so this is an interesting part of the argument. So basically the way I do this is I prove this statement in blue. Okay. Because, I mean, we've basically just made this chi of m, this classifying arrow of m. We've shown that pulling back true along chi of m gives us something equivalent to m. So I mean, it might as well, we could even say it gives us m. It's just up to us which one of those equivalent sub-objects we want to actually think of as the pullback. Like, we like to think of inclusion monics because it makes everything kind of canonical. But you know, essentially, you can get any monic then. You know, you can. We've basically described how we can make this classifying arrow, which is such that we can pull back true along this classifying arrow chi of m to get our m. But we need to show that that kind of classifying arrow is unique. So the basic way I sort of think of this is, well, what if we use something different? What if we used an arrow which worked differently, a different arrow into omega? Well, we get something different. Okay, this is what I want to establish. And so I just prove this result, which essentially infers what we want. And this result just says that if we have a pair of different arrows, G and G dash from A to omega, well then, if we pull back true along G, then we get a sub-object of A which is different to the pullback of true along G dash. Okay, so basically I'm saying if we pull back true along different arrows into omega, we get different results. We get fundamentally different monics. And clearly then that'll mean in our case that for our we've made this particular chi-m that works, but this would show that if we used anything else, it wouldn't work because, you know, when you've got distinct parallel arrows coming into omega, if you pull back like G and G dash here, if you pull back true along G, you'll get a fundamentally different sub-object to if you pull back true along G dash. And so this kind of shows that only one arrow from A to omega can, you know, make it so that if we pull back true along that arrow, we get M or something equivalent to M, like back in the original case. But we're just talking now about this sort of, in some ways, more general result, which just says that, you know, if you want to get the same result by pulling back along arrows into omega, those arrows better be the same. Or sort of the contrapositive, which is really what I'm proving here, is that if G is not equal to G dash, then the pullback of true along G is not equivalent to the pullback of true along G dash. So how do we establish this? Well, this turns out to be the kind of So this turns out to be the key sort of thing to it. We have that for an arrow R from E to W, we have that this is going to be in GE of theta, or maybe I should say R under arrow is, well, yeah. Okay, let me say this more precisely. For this arrow RE to W, we're going to have that R under arrow is going to be in G of E of theta. So here, theta is an E-type element of A, and we're thinking of GE of theta now as a kind of sub-object of hom E comma blank. Anyway, we're going to have R underlined and arrow is going to be in G of E of theta if and only if the pullback of G of E of theta along H of R is equal to this maximal subobject of hom E of hom W. Okay, so this is just the identity arrow of hom W comma blank. So firstly, I ought to establish this. Let's just underline it. So I actually establish it. I write, because the notation gets a bit busy, so I denote this G of E of theta as X. Okay, so X is just a sub-object of hom E comma blank, and R is an arrow from E to W. Or if you like, we can think of R as a W-type element of hom E comma blank. And so R under arrow is going to be this arrow from hom W comma blank to hom E comma blank. And now we can see that we're going to have that R under arrow is in X if and only if the identity of hom E comma blank after R under arrow is in X, if and only if the identity arrow of hom E comma blank is in the pullback of X along R under arrow. And now something interesting, which I think I neglected to mention so far, but R under arrow is equal to H superscript R. Okay, so this is a general kind of thing that's true. You can check it by thinking, like, so this hasn't got anything to do with these particulars. This kind of thing's always true. And you can check it just by looking at the components of you can check it by just looking at these things as kind of like natural transformations with components that are functions, and think about one of those functions working on a general input, a general component function, and you'll see that these things are actually equal. And so this fact means that actually this happens if and only if hom E comma blank is in H to the R to the -1 of X. And this obviously happens if and only if well, this identity arrow, we can equivalently write it as hom of psi e comma t, and this only happens if it's actually equal to the pullback of x along h of r. Okay, because the only way the identity can be in the monic is if it's equal to the monic, or equivalent to it at least. So yeah. Except I made a little mistake here. This is supposed to be a W. Now it all makes sense. Yeah, so using this kind of result with x equal to g e of theta, we essentially prove this kind of thing in this red bubble. And then actually this is just equal to the effect, it's equal to the outcome we get when we just do an R action on G of E of theta in omega. And since G is a natural transformation from A to omega, we can rewrite this as G of W of AS of theta. And we can rewrite this as K. So here we've sort of found a G. So the sort of crucial thing here is that given this kind of R under arrow in G of E of theta, we can find this kind of K such that GW of K is this psi W of T thing here. Now, here's the thing. Suppose now that G is not equal to G dash. Well, then there has to exist some E-type element theta such that GE of theta does not equal GE dash of theta. Now, these are both just subobjects of hom e comma blank, but actually we're saying they're non-equivalent, so they ought to have different things in them. Okay, so that means, you know, there's going to be like some like W type element of hom e comma blank, some basically corresponding to an arrow, r under arrow, such that, you know, we're either going to have that r under arrow is in g of e of theta, but r under, in which case, you know, we can find a k, yeah, so we're either, so there's going to be, in this case then, there's going to be some r under arrow, which basically just corresponds to a kind of w type element of hom e comma blank, which we're going to have, like, it's either going to be the case that we're going to have r under arrows in g e of theta, but it's not in g dash e of theta, or vice versa, it's in g e dash of theta, but not in g v of theta. So, like, let's suppose the first case, let's suppose that r under arrow is in g e of dash of, it is in ge of theta, but it's not in ge dash of theta. Well then, since r under arrow is in ge of theta, this kind of argument says that we find this k is equal to as of theta, which is, we're going to have the case that gw of k is psi w of t, but that's not equal to g dash of w of k, because r under arrow is not in g dash of w of k. So again, this sort of if and only if argument would say that, yeah, in that case, like, this won't be equal to this kind of maximal subobject thing, or alternatively, there exists a k such that g dash w of k is psi w of t, but that's not equal to gw of k. So this is the alternative case. I mean, all we're basically saying here is we're assuming that we have different subobjects of hom e comma blank, but I'm saying that if they're different, then they must differ by the presence of some essentially some w type element, or if we like, an arrow corresponding to it under the Oneida correspondence, and you know, such a thing will be present in one but not the other. And then this kind of argument allows us to find a k such that we're going to have that, you know, k is actually not a of s of w. Whoops. It's a of r of w, isn't it? Yes, excuse me. Yeah, so sorry, we can then, you know, using the naturality, we can find this k, which is a of r of theta, and we're going to have that gw of k is equal to psi w of t, whereas that's not equal to g dash w of k in this case where r under arrow is present in here, but not in here. Sorry, it's present in here, but not in here. Or alternatively, if the r under arrow is present in here, but not in here, then we're going to have this case. Either way, we can get by. But here's the thing now. Remember now from our classifier theorem 1 that the actual subobject obtained by pulling true back along G, if we think of it as an inclusion monic, then its E-type elements are going to be the set of E-type elements of A, such that G E of theta is equal to psi E of t. And there's a sort of analogous result, of course, for G dash. But then we're saying that, well, you know, in either of these two sort of cases, if there is a sort of W type element K, where, you know, we've either got GW of K is psi WT, but that's not equal to G dash W of K, or, you know, this case, which is the sort of other possible case where, you know, we have the G dash thing's equal to psi WT, but for G1 isn't. In either of these cases, we can see that if we look at the type W sort of sets involved, so this kind of case where E equals W, these two sets are going to be different. And that means that our inclusion monics are going to be different. And that means that, yeah, in this case, you know, because the inclusion monic, you know, it sort of canonically represents this class of equivalent monics. If two monics are such that the inclusion monics, which are equivalent to them, so say we have two monics A and B, and we find the kind of inclusion monics A and B dash, which are equivalent to, you know, we find, so, okay, let's say we have a monic A and we find the inclusion monic A dash, which is equivalent to it, and we have a monic B and we find the inclusion monic B dash, which is equivalent to it. If it happens that these two inclusion monics are not equal, then that implies that A and B are not themselves equivalent, okay? Because, you know, this kind of inclusion monic's like a kind of canonical representation of this equivalence class of monics. So the fact that at the end of our argument, we've basically got that this pullback of true along G represented as an inclusion monic gives us something different to the pullback of true along G dash. That means, you know, however we do these pullbacks, when we pull back true along G, we're going to get something that's not equivalent to the pullback of true along G dash. And so that proves our result. Where is it now? Yeah, that proves this result. And that essentially proves that the chi-m, which we've constructed, is the only one that works, because anything else would lead to a different subobject. So yeah, that now shows that we have this unique arrow chi of m from A to omega, such that the pullback of true along chi of m gives us m.